So in this problem we have a platform which is oscillating vertically with simple harmonic motion with amplitude A and frequency nu. Now part A of the problem, we're going to place a block at the lowest on the platform at its lowest point, and we have to find the critical frequency such that the block will remain in contact with the platform throughout its motion. So first, let's draw an isolation diagram of the block. So we're going to define the upwards direction to be the positive y direction. So the normal force acts on the block in the positive y direction. And we've got the force of gravity acting in the negative y direction, which is given by mg, where m is the mass of the block. So by Newton's second law, we have that our equation of motion is the net force in the y direction is going to be given by n minus mg, and that's going to be equal to the mass times its acceleration in the y direction, which is going to be y double dot. Alright, so this means that n is equal to my double dot plus mg. So in order for the block to remain in contact with the platform, the normal force must be greater than or equal to 0. Now, since mg is a constant, this means that the value of n depends on y double dot, the vertical acceleration of the block. So when y double dot is at a minimum, n is at a minimum. Now, to figure out what the minimum value of y double dot is, we first have to have an equation of motion for the block. So we know that it's simple harmonic motion, which means its motion is governed by a trig function. And its amplitude is big A, so we can write its equation of motion as A times sine of omega t. So this will give the position, the vertical position of the block, where we've taken y equal to 0 at the midpoint of the block's motion. So this means that y dot is going to be given by omega a cosine omega t. So y double dot is just negative omega squared times a sine omega t. Now sine falls between -1 and 1. So the minimum value of y double dot is going to be equal to negative omega squared a. Now, we know that at the critical frequency, so at the critical angular frequency, the minimum value of the normal force is 0, which means that my double dot, or my double dot minimum at the critical frequency is going to be equal to negative mg. So in this case, this implies that if you plug in for the minimum value of y double dot at the critical frequency, then negative omega squared, omega critical squared times big A is equal to negative mg. So if you solve for omega, you see that the negatives and the m's cancel out. So omega critical is going to be equal to the square root G over big A. So at this critical angular frequency, at the minimum value of y double dot, the normal force will be equal to 0. So this means that the critical frequency, mu critical, is going to be equal to omega critical over 2 pi, which is just 1 over 2 pi times the square root of G over big A. So that's our answer for part A of the problem. Now in part B of the problem, we're going to assume that frequency is greater than the critical frequency, and we're asked to figure out how far above the lowest point of the platform does the block leave the platform. So in this case, when the normal force is 0, that's when the block leaves the platform. So we have to solve for when my double dot is equal to negative mg. Now notice that y double dot, which is equal to negative omega squared a sine omega t, can also be written as negative omega squared y, since y is just a sine omega t. Which means that y is just given by negative y double dot over omega squared. Alright. So this means that we know that y from this equation can cancel out the m's. It's going to be negative g, which means that y is equal to negative g, or negative g, which is just positive g, over omega squared. And we know that omega is 2 pi times the frequency. So I have that y, the vertical distance at which block leaves a platform, is given by g over 2 pi mu all squared. Now this is, y is the vertical distance of the block from its midpoint of its motion, which means that the distance h from the lowest point of the platform's motion is going to be y plus big A, where A is the amplitude. So the final answer is g over 2 pi mu squared plus big A. So that's the distance that the block will leave a platform from the lowest point of the platform's motion.